Everyone, welcome to APEC. It's January 16th, and I'm your moderator, Tim Ventura. First, I would like to thank everyone for joining us today on this call, and I want to do a big shout out to everyone watching us on YouTube live stream as well. I'd also like to thank Mark Sokol and the Falcon Space team, and give a giant thank you to today's scheduled presenters, Ron Evans and Nick Pope. Ron will be presenting on the BAE Greenglow project, and we also have Rob Chambers here. We're going to try and squeeze him in if we have time. He has some stuff to present as well. And Nick Pope is going to be joining us in about 2 hours to talk about UAPs. After that, Mark will be showcasing some progress on his latest projects and again, showing us around his lab. I have a couple of quick announcements, and this is mostly for our YouTube viewers. If you can, please take a moment to sign up for our email announcement list. Right now, I have a copy of that up at americanantigravity.com/events. Again, that's americanantigravity.com/events. Now, since I'm speaking of websites, Jeremy Reese has also been updating alienscientist.com. And again, he live streams this on his channel. He's got over 100,000 subscribers. So take a moment and visit him at alienscientist.com. And we are also in the process of building a brand new dedicated APEC conference website, which should be finished in the next week or so. So again, thank you to everyone for joining us, and let's welcome Ron Evans to the call.
Okay, away we go. I've got my scarf on because some people recognize me with the scarf. And I wear the hat because I am bald. I'll show you all, but it keeps me warm and I like to have that on. Right, so Greenglow. First of all, I'm going to read from my notes. So thanks to Tim for inviting me, and I'm wishing everybody a happy new year. I expect Tim has already done that. So this is going to be about Project Greenglow, which is anti-gravity or gravity. And I've got some further ideas, which we'll hear about towards the end. I joined British Aerospace in 1978. Long time ago now. When I arrived, I was an expert in fluid mechanics. So, and I had been working at university on an investigation looking at wings with vortices coming off them, because it was quite clear that the next aeroplane was going to have four planes. Makes the aeroplane lighter, but then you've got the vortex from the main wing interacting with the foreplane wing. So I'd been working on that. I applied to work at BAE, that's Walton. That's, if you know the geography of England, it's North England near a seaside town called Blackpool. I was hoping to work with the fluid mechanics, computational fluid mechanics group, because they'd been working on the same things. But I didn't end up there. I ended up working for the group which was involved with performance and propulsion. And I, in fact, ended up in the drag section. So it was quite, well, I hadn't been expecting that. Most of the time, where are the slides, Tim? Okay, so we've seen that one. We can move on to the next one. Now you can see my scarf. So I'll just say next for next, okay? Right, so we're now into the analogies of physics. Now, I'm a mathematician. Mathematicians love patterns. It's not that we're lazy, because once we've got something, we can just change the symbols and it means something else. So on the left-hand side here, we have the fluid mechanics model. So the blue circle is a source. You can imagine a kitchen tap and the water pouring out. That's a sort of one-dimensional source. When it hits the floor of the sink, it spreads out in 2 dimensions. And the blue lines are the streamlines, and you can put dye or milk or something in to actually see them. And we can have a sink, which is just all the water going back in this time. We can have a vortex, and you've all seen the vortex. Well, these days everybody has showers, I suppose, but if you have a bath, you see the vortex going down the plug hole. If you grab hold of that green vortex, with your fingers going round in the direction that the water goes round in, your thumb will point in the direction of the vortex. And that's called the curl of velocity. And we can have a smoke ring. sorry, I'm just reading a message from Gary. Right, so that a smoke ring. And there, if you look carefully, you can see that the fluid going in one side and coming out the other. So it's like having a source and a sink. They will give you the same flow pattern. The middle one is electromagnetism, when we can have a positive charge where the electric field lines go outwards, and we have and also a negative charge. And again, we can have a current flow, and this time we get a magnetic field around the line. That is very similar to the vortex. And at the bottom, we can have what looks like a smoke ring, but this time it's a solenoid, and we can have a virtual source and a sink. Now, the next one is gravity. In fact, gravity was the very first one that we had, but we only had it for static situations. And we only know about mass, which is an acceleration sink. Whether we can have an acceleration source or negative matter, nobody knows. Everybody thinks, well, a lot of people think it's not possible. Some people think it might, and there have been other ways of making such a thing. Now, if you move mass going along with the other analogues, why don't we get a gravitomagnetic field? Perhaps we should do. No one's ever seen it, not in a laboratory on Earth. And if we have a spinning mass, then that's going to look like a smoke ring or a solenoid. So why didn't anybody ever see the gravitomagnetic field? And why hasn't it been made use of? The reason it's not been made use of is because somebody called Gottfried Leibniz, another man who created calculus at the same time as Newton, introduced something called vis visa. It turned out that vis visa, which was just m times v squared, but if you took a half of it, it turned out to be the kinetic energy. We didn't need the gravitomagnetic field, so it wasn't detectable as far as anybody knew, but we could do without it anyway, so why bother? Newton didn't understand energy. Well, he certainly didn't make use of it, and he wasn't bothered about vis visa. But Newton's mechanics developed with kinetic energy. Well, let's go on a bit further, but just to say, if you change the velocity, you'll get an acceleration. If you change it here, you get an acceleration, and that acceleration of a magnetic field gives you an electric field. If you knew about the gravitomagnetic field and you could change it, you would create a gravity field. Well, that's what we want to learn about. But working with kinetic energy doesn't tell us anything about it at all.
Now, Ron, would you like me to go on to the next slide, or are we still on this one?
Next slide, please.
Absolutely, sir.
So as I was saying, when I came from university, I'd hoped to work with the fluid mechanics group, but I ended up in the drag section, probably because the boss of the performance group was actually another Leeds graduate. And since I was a Leeds graduate, you probably thought, oh, right, I know this sort of person, I'll take him. And I ended up in the wind tunnel. It was interesting. It was all data analysis. You're a mathematician, you do it. Next slide, please. In 1979, a photograph was sent to the publicity department to somebody called David Camillard, who was head of publicity, and he didn't know what it was. Very strange looking craft. He asked the aerodynamics people. Actually, I didn't see it, but they sent it to the chief aerodynamicist, and he showed the deputy chief and other people. Nobody knew what it was. The next year, the chief aerodynamicist had to go down to RAE Farnborough, just south of London. It's where all the research was done right from the First World War on aerodynamics. And at the meeting, which was given by somebody from the United States, they were told all about the 117, and all its strange shape. So we now knew what it was, and it had actually been flying over the North York Moors. Nobody knew what it was. It was a UFO, a real UFO. Well, the chief aerodynamicist came back and thought, right, we need to make sure we've covered this. I was one of the last people in the department. I was a mathematician. I'd studied electromagnetism. Oh, right, we'll use him. Go and find out about stealth program and set something up for us and make sure everybody in the aerodynamics office is well aware of what's going on. So I was given the job. And the first thing I did is I looked for the reports, and to my surprise, in a way, I realized that the United Kingdom back in the 50s, even the late 40s, was an expert on stealth. All our bombers at that time had stealth features put on them, mostly RAM. The RCS paper on was secret, is now unclassified, but it described all the work that had been done back in the 50s. And I actually met the man who was responsible for the program. You can see his name on that report. It's Grant Dawson. So the middle slide is the scale model radar range down near Bristol. And so I went there, and wow, they had lots of scale models, and it was well used by the United States. I met several Americans there at the time. So they were well into stealth by then, but of course they'd already got the F-117. I don't remember seeing an F-117 model there. I may have done. I certainly don't remember. Anyway, the mathematician I met down there was Dudley Bird, and the man that was responsible for a lot of the work was called Sid Woolcock. I don't know whether any of you had any work on the stealth side, a name you'll maybe recognize. The next thing I did is I went to the Plessy company down at Towcester, which is sort of down in the south west of England. And they make radar absorbing material. And I met somebody there called Bernard Wickenton, who had actually been to Germany at the end of the war to see how the Germans made RAM, because they'd been using RAM to line up the leading edges of their night fighters, because they knew darn well that's how the British fighters were catching them. And also they'd been using RAM on their submarines because they knew they'd been caught on the surface with their snorkels and conning towers. They were all covered in RAM. Okay, so next slide, please. Okay, right.
Okay.
I got a phone call in 1983 to say, you're going to be moved to the Advanced Technology Group. I said, no, I don't think so. I'm running the stealth program. So I went to see the chief aerodynamicist and said, I don't want to go. He said, well, you've got to. You're a mathematician. He said, I've got plenty of managers, but we haven't got very many mathematicians, so you'll have to go. So I did. And the man in charge was called Tom Smith. In the 50s, he'd been working on what was called Mustard, which was a multi-unit space plane. And there's a model of it in the Smithsonian Museum in Washington. Later on, in the 1960s, he headed the HOTOL program. You may have heard of them, I don't know. But there we are. There was the radar, millimeter radar system. The idea was that they were going to fly this and pick up the signature of tanks and be able to actually identify them. British Aerospace wasn't the only company working on this. There was another company called Marconi in the UK and several companies in the United States. And they all got together and compared data. Well, they tried to, they couldn't. There was something wrong. All the data that they'd collected on tanks all seemed to be different. So my job was to go through the data analysis that we'd collected and try to put it into some form that could, and then collect other people's data and match it. So that's what I did. I spent some time doing it, but eventually I came up with a method and we could then investigate everybody's data and check it all out. So that's what I did. After I'd finished doing that, I had to work on several other things, which I can't mention really. But anyway, I went to the boss and said, you know, we've spent all this money on stealth. Maybe somebody clever is looking at using the gravitational signature of something. I mean, you can see a ship, a battleship, using it with gravity at 3 miles. Okay, an aeroplane's a bit more difficult, but as we'll see towards the end, the MOD have come up with some ways to look at signatures, and McDonnell Douglas back in 1991 were also trying that system. So we knew it was possible. So I said to the boss, you know, can I go and check this out? I said, yes, if you think it's worth it, you do that. Next slide, please. So the first thing I did is I went to talk to a professor at Imperial College in London, who back in 1974 had given a presentation at the Royal Institution in London. The Royal Institution was made famous in the 19th century by several people, but the first two was Sir Humphrey Davy, and the person who really made it famous was Michael Faraday. So the Christmas lecture by Eric Laithwaite was all about gyroscopes, amongst one thing. Professor Laithwaite thought that gyroscopes could be explained by something that we now call the GEM equations. If you look at the slide, you may recognize Maxwell's equations at the top there. And there's those curl terms that we looked at right at the beginning, and you now know what a curl is. It's just you grab hold of the whatever it is and twist your fingers around in the direction of either the magnetic field, the fluid lines, or the gravitomagnetic field. So there we are. Let's look at the GEM equations. And the first one says curl of gravity equals the change of the gravitomagnetic field. That's the H. The next one to it, which is that upside down delta with a dot G, is in fact Newton's formula. That's Newton's only bit. So in Newton's gravity theory, that's the only bit. All the rest isn't used. That's because we don't use gravitomagnetism. We use vis-vis or kinetic energy. Now, what we want to find out is, can we find out what gravitomagnetism is? Can we jiggle it? Because if we can, we might be able to create gravity. Now there's equivalencies. You'll all be familiar in terms of gravity is equivalent to acceleration. If you're in the lift and it accelerates upwards, you feel heavier. So that's an acceleration. Gravity is a field. You can make an effect across space and have an effect on a mass. You can't do that with acceleration. You actually have to push on the mass to make it accelerate. So though they're equivalent, they're not the same, because one's got field properties, the other one hasn't. Now we come on to H, or gravitomagnetism. That is equivalent to angular velocity. If you've got a gyro and you spin it, it's got angular velocity. But to make that spin, you have to actually spin the mass. But gravitomagnetism has a field property. Why can't we see it? It's so incredibly weak because, let's go back to magnetism. Magnetism, if you look at the first equation, curl E, it's got a mu sign there. That's the permeability of the magnetic field across space. Now come on to the analog down at the bottom, curl of little h, and you can see there's a gamma. And if you look afterwards, there's what's called B equals that peculiar sign, which I call eta. B equals eta h, which is at the bottom on the right-hand side. Now, if you're looking on the right-hand side of the picture, the speed of light squared, I'm sure you all know, is 1 over epsilon mu. That's the permittivity of electric field in space times the permeability of the magnetic field. And underneath there we've got c squared. Again, the speed of light squared. That's 1 over gamma, which is, I prefer gamma, it's a better feel for me, but gamma is equal to 1 over 4 pi big G. That big G is Newton's inverse square effect. But notice that if we look at c squared, I've got 1 over gamma times this, what I call eta. Now that eta is the permeability of the H field in space. Turns out to be absolutely tiny. Next slide, please. We had a chance to, or what I didn't mention to you was Professor Lathwaite got in trouble because he demonstrated an inertial thrust machine. And there were a number of academics in the audience that didn't believe it. One of the inertial thrust machines that was around at that time was called Kidd's inertial thrust machine. He was a Scotsman who lived up near Dundee. Kidd wasn't the only one. There were a number of other ones. Some of them had actually been patented. So Kidd was quite willing for us to test his device at Wharton. So it was on the news, it'd been on television. So we tested it. There's a picture of it at the bottom left-hand corner there. It was 2 gyros which waved around, up, waved and span, and they joggled up and down. And in throwing themselves up and throwing themselves down, they created enormous accelerations. But did they actually change weight while they were doing it? We put it on a bungee because the bungee would just damp out the accelerations. We weren't interested in the size of the accelerations. We were interested, was there any change of weight? And we did the tests, and the top one there, you can see that within the error band, we couldn't see anything at all. On one occasion, they seemed to be outside the error band, seemed to say, oh, bit strange. We weren't sure. So that was 1 out of, I forget how many, 20, I think, that we did. It was July 1991. There was no way, as we will see later, we could carry on doing any more. So we weren't very good scientists. If you have an anomaly, a good scientist will keep poking it to find out what caused it. So unfortunately, we weren't able to do that. Next slide, please. Now, in 1989, I think, 1989, I had an opportunity to go and visit Dr. Robert Forward. Now, if you know anything about gravity studies, Robert Forward has been one of the people that's been pushing it, he's a pioneer. And, so I went up right to the north of Scotland. You may have heard of the nuclear power station there, Dounreay. Well, he lived in a cottage at Ray, which was actually just near Dounreay. He wrote a paper in, oh, I should say, he got his PhD working with Joseph Weber, working on looking for gravity waves. Joseph Weber had come up with a long metal cylinder, rather like an antenna for detecting radio waves. They also came up with another device which they called a gravity interferometer, which was actually built where Robert Forward was employed, which was at the Hughes Research Laboratory at Malibu. That's another story. So Robert Forward had written this paper saying, theoretically, it should be possible to create anti-gravity with, I put the picture at the bottom there, with a toroid. And with the toroid, if it's electric, it will create a magnetic field inside. If you change the electric field through the toroid, then that blue magnetic field will change. A changing magnetic field creates a gravity field. And that gravity field I've shown, an electric field, a changing magnetic field creates an electric field, which I've shown by that straight line, black line there in the center. And he gave us a model, which when you check it out, it's an approximation, but it's perfectly theoretical. But there are some theory, you have to make assumptions. And at the top there is the electric field that you create. And I've put E epsilon mu, that's the free space value of the permeability of magnetism. and mu r is the relative permeability. And that's the changing current. And there you are, a squared is the radius of the electric lines there in the toroid, and r is the radius of the whole toroid. Okay, I'm just reading that. I'm not sure what that's about. Now, Robert Forward talked about changing those electric toroid and having a big piping and passing fluid through it, but he said it was impossible. However, if you think about it, electric charge has got both charge, but it's also got a gravitational charge as well, because an electron has an electric field and it has a gravitational field. So you could, I put it in, now that's not in his paper, but it's perfectly feasible to write it like that, where again you've got eta naught. Now that eta naught is 10 to the minus 20, sorry, yes it is, 10 to the minus 26. This is why Forward said it won't work. But notice the relative permeability. Now that, probably small, but we don't know what it is. If we go to the one above it, the mu r is the relative permeability of magnetism. Generally, that's between 0 and 1. For a superconductor, it's 0. For most materials, it's about 1. But for some materials, like a material called mu metal, it's 50,000. 50,000 is a bit different to 1. Now, we don't know about eta r. There may be materials which have properties of 50,000. That suddenly starts to make a difference. They might be more than that. They might be 50 million. I don't know. Until someone is able to look at a gravitomagnetic field and start poking it about, we won't know. So in my mind, I have wondered, you know, Robert Forward, did he go back to the Hughes research place and say to somebody, oh, I wonder whether it's possible to change that eta r and make something work. And then we would have a gravity field created too. Next slide, please. My boss, Tom Smith, retired in 1990. As we'll see later, a lot of people were retiring. In 1977, the aerospace companies were nationalised, but were denationalised in 1977. So in 1978, when I joined, it had only been denationalised 1 year. All the time, the company was changing, trying to get itself sorted out. In 1990, Tom Smith had been working for what was first English Electric, then British Aircraft Corporation, finally British Aerospace. And in 1990, after 40 odd years, he retired. So I got a new boss who decided to call it something new. He called it Business Strategy Department, or British, no, it wasn't. It was called the Future Business Strategy Group. By that time, I'd been working for Tom, and Tom Smith had allowed me to investigate this gravity side. And I'd organised a meeting with several universities within the UK. And we'd come up with a meeting in March 1990, and there's the list of things that we studied. So gravitational wave research was very popular. I mean, would it ever be possible to use gravitational waves to detect aeroplanes? I mean, that's a bit like the work that Gary Stevenson was working on with his high frequency gravity waves. Fourth experiments at that time in 1990 were in the news. The superconducting gravity gradiometer is a way of moving submarines, for instance, without having to make any noise with your sonometers or anything like that. I was more interested in Faraday's gravity experiments. very few people seem to have followed it up. There was the quantum effects in microgravity, which has gone on in the past 20 or 30 years. I was again interested myself in Heaviside's linearized gravity theory and the gem equations. These gem equations were first studied by Maxwell himself. He wondered, having developed the electromagnetic model, well, why it looks very similar to gravity. And he'd pondered over it for a while, and then he busy starting other. He had to start the Clarendon laboratory in Cambridge. He was far too busy to bother with it too much. Heaviside was a mathematician in the 1890s. He had a look at it, but decided that parameter, that field, the eta, the permeability, was too small. So he didn't pursue it either. We had somebody coming up from Kent who looked at a new model of the electron, and we had somebody from Birmingham University looking at gravitational things. So it was all ongoing. It was very interesting. I published the report. Next slide, please. And that report was sent off to the library, and the library put it on the exchange with NASA. NASA had an exchange agreement with British Aerospace, and they would swap documents. So that went off to NASA. I don't know what we got back in return. Well, in fact, I do. We got back a report called an electric propulsion study, which actually looked at more than I'd done. I hope you all know about the electric propulsion study. It's on the floor down there. If you haven't asked me in questions and answers, and I'll tell you about it. Now, what I hadn't realized is that the technical director, who was a nuclear physicist originally, he was quite interested in my report, and he wanted it because he was going to be made a professor at Salford University. Salford is where the British Aerospace apprentices went. Just check my time. What am I up to? I need to get a bit of a move on. So he asked me to tell him about it. I showed him and he read the report. He sent me off to Salford to talk to the people there. I explained it to them and they said, oh, yeah, that's all legitimate. I went back and told him. He said, good, I'll go and give it. I didn't want to be made a fool. And there he asked the people in the future concepts, they draw me some pictures, draw me a GA, and I'll take those with me. Off he went. It went down so well. He came back. He was so pleased with himself. He gave the lecture at the Institute of Mechanical Engineering in London. That got publicized, went to the press. Then he had an interview on the radio. Next thing he knew, we had all sorts of people asking him for more information. And that's where Nick Cook came in, because Brian Young, who was the technical director, said to Nick Cook, you go and talk to Ron Evans. I think he'd had his fun and he didn't want to be involved with any more. So Nick came and talked to me, or rather I went to talk to Nick. And later on, the Hunt for Zero point appeared where Nick mentioned the BAE program, but he was more interested in what the Germans had been doing during the wartime, and also what the United States had been doing. Would anybody tell him, were they working on stealth? By and large, they wouldn't. He came back to thinking, well, maybe they are, maybe they're not. Next slide, please. So I'll go to this very quickly. As I said to you, we were still restructuring. 1990 was a very difficult time. So that BAE was selling off things left, right, and centre. They were still the biggest exporter for the United Kingdom. They were having talks with DASA about merging. Early on in the year, they thought they might have been bought by GEC, but they managed to get through that. And then in 1999, they managed to buy Marconi from GEC. And then in 1999, that became BAE Systems. So there were a lot of changes going on where I was working, and they closed some of the sites, and there are other sites. In fact, if Rob Chambers is there, perhaps he will tell us whether they closed Plymouth at that time. I can't remember when they did. So 1990, I was in the Wharton Advanced Technologies side. I'd got a small group doing various things. Everything was very part-time. We were lots of studies going on. I remember a four-legged robot walking around the department at the time when all the problems going on. It wasn't looked on very favourably. Next thing I knew, the exploratory studies group had been closed, so I'd had to get another job. I'd only got another job for about a year, and then that was closed and I had to look for another job. I thought I was going to be made redundant. Fortunately, the person who had taken over the stealth group that I'd started said, well, come and work with me. So I went to work for him. That was lucky. Then in 1995, there were so many people wanting to be managers that the technologists career branch was started. So I ended up being an advisor. Mathematicians aren't seen as specialists. They're sort of generalists. So next slide, please. Right, I think we can just go through this very quickly, but this is really the start of Project Greenglow. Because with the technologists, they'd actually got a little bit of money. In 1980, again, with all the company in flux, really, Wharton had a lot of research money at the time. In fact, when I'd responded to the interview in 1977 to apply for the job, they were the biggest research and development aerodrome in Europe, and they had a lot of research money. But in 1980, the headquarters in London decided, no, we've got what was the Missile Research Centre in Bristol. We're going to make that the BAE Research Centre. So we want the research money from Wharton. We'll send it to Bristol. And if Wharton want to do research, they'll have to go through Bristol and get it done down there. So they'd lost a lot of money, but the technologists had got a little bit of money back. So in March 97, I'd got John Allen, who had been made redundant or had actually taken early retirement from Kingston. Kingston was where the Harrier and the Hawk were built, but they'd closed that site and all that work had been moved to Wharton. But he came up to talk to us about the future of aerospace, and he talked to the future concepts engineers. And John, back in 1970, had written a book, and in it there was a chapter about gravity. He was very keen on gravity. His boss, whose name escapes me for the moment, wasn't too keen on John talking about gravity. Like so many bosses, it sounds like anti-gravity, and they're all scared stiff of anti-gravity. So that went very well. I asked John to do a study for us, and that's this blue report on the right there. Supposing we had an anti-gravity engine, how would it change aerodynamics, vehicles? So he went away and did that for us. That later became an AIAA paper. Also at the same time, I went to our local university, University of Central Lancashire, got a professor there to do a study. Faraday had been very interested in heat experiments, so I got him to do a study. It actually turned out to be something that had already been discovered back in 1897 by somebody called Leduc, but I didn't know that at the time. Then I went to a meeting with Robin Tucker at the University of Lancashire. Professor Robin Tucker was a professor of gravitational physics. So if anybody should know about anti-gravity, he should. He was a bit wary, but tackling it from an Einstein's general relativity side, he thought it was worth having a go at doing something. They had a team there of 4 or 5 general relativity people. So he suggested, why don't we come up with a joint program? We'll fund part of it, or we'll get money to fund it, and you'll have to fund the other. So I went back to the technologists, I proposed a program, and it was agreed very quickly, and we got something started. Robin Tucker became the academic advisor. So quite clearly, British Aerospace was not doing the research work. The research work was being done at United Kingdom universities. So Robin was the academic advisor. John Allen was going to be the design consultant. Now that might be done by BAE. So in 1997, that began the start. It was all funded. We had some small support from Rolls-Royce. We started with a lecture series. We had a couple of academics from Greece, Athens, I think. My goodness, we had a big audience from MOD, from Rolls-Royce, from BAE, MOD, and those academics were given a hard time. Then in 1999, MOD contacted me and said, look, you should really be having a look at a photon drive. It's work that was done by the Soviet Union. And one of the people that worked on it was Sergei Vinogradov, then at Kharkov University, part of the Soviet Union. He's going to work with Paul Smith. So we got some funding from that. And then along came Podkletnov. It was all in the news. And then I learned that students at Sheffield University were also studying it. I don't know whether Clive is in your audience, Tim, but he will know. I went to Clive Woods and said to him, perhaps we could fund a little bit for you to check it out. And he agreed, a good idea. I've put a picture of Podkletnov's part of his device. The brown is his superconducting ring. It was the YBCO ring, yttrium barium copper oxide. It's called a type 2 ring, which becomes superconducting, getting near to room temperatures. And then those 3 solenoids are the thing that make it work. Now you're going to have to cast your mind back to that toroid. That, in fact, is a part toroid, isn't it? If I filled in the spaces, it would be a toroid. And what did Robert Forward tell us? That if you change the current, it created both an electric and a gravitational field. Now, Dr. Podkletnov had put his device in a metallic container and made it superconducting. It was metallic, it was a Faraday screen. No electric field could get out, but you can't screen against gravity. So maybe gravity did get out. Maybe yttrium barium copper oxide is this very thing we're looking for, the permeability of gravitomagnetism with a high value. I don't know. So on the right-hand bottom corner is one of Clive Wood's reports. Next slide, please. Right, we're halfway and I've only got a quarter of an hour to go. So John Allen did the study for us. I've mentioned that already. Done that, we've done that. Right. To Dundee. Right. Sorry, I'm just having to remind myself what I'm going to be talking about. So 1999 saw the formation, November 99, it wasn't really until 2000 that BAE Systems was formed. And everything came to a standstill in terms of research. All the money that we had at Wharton was frozen. So although the universities that were doing work, they carried on, we couldn't pay them any money. So the ATCs that were now, so that what had been the original British Aerospace Research Centre now joined with what had been the Marconi Research Centre. So the British Aerospace one at Bristol had dealt mostly with aerodynamics. They'd also, I mean, when I'd run the stealth program, I'd arranged to get stealth signatures, a program called G58. So we were starting to predict from modelling what the radar signature was. All that work went down to Bristol, and the team, I'm afraid, at Wharton had to go and find other work. But the people at Bristol, I better not say any more about this, I shouldn't really. So the team at the Baddow Research Centre, was at Great Baddow, which is in Essex, which is in southeast England. They were really working on electronics and systems and things like that. So between the two of them, they decided they shouldn't be funding Greenglow until they'd had their own look at it and had some assessment. So they had an assessment done by Glasgow University, and that's that blue report there. So that took a bit of time to do, and that had to be funded by the ATC, which included both of them, and it also included Rolls-Royce. They were interested to know what was going on, so that was funded. The report came back and they said the Greenglow thing was really looking more at gravitational and gravitomagnetic fields. It was a field study. They thought it should really be more, or they ought to have more about the quantum aspects of gravity. And I think the reason was, about that time, Hal Puthoff and his colleagues had been looking at inertia and saying it could be a quantum effect. Anyway, the universities agreed to fund what Walton had already started on, and we'd have to get some quantum work. So I managed to get people at Birmingham, Professor Clive Speake now, looking at Casimir study. They're actually using a superconducting gravity gradiometer, but they could do a Casimir study by the side with it. And the Lancaster University people, they went off to New Zealand to look at the gravitomagnetic field around the Earth. I'll say a bit more about that in a minute. And in 2000, we also got Mark Millis to come and give us a talk about what they were doing on the NASA Breakthrough Propulsion Physics program. And then we told them what we were doing. In fact, at the time, well, I'll just tell you what happened. At the end of all of it, we were all getting on very well together, and Mark Millis arranged, I think it was probably through what was called EOARD, which is an American centre in London looking at all research going on in Europe. And the people at EOARD agreed to fund the university people that are working at Walton to go and give their work, results of their work in the United States. Why United Kingdom can't fund things like that, I don't know. Sorry, I shouldn't be saying this. Not very good for UK. But UK will work on some things. The UK MOD supported what we were doing, but they were scared stiff it would be seen as a UFO study, and they couldn't afford to be mixed up with UFOs. Maybe Nick Pope might tell us something about that. In 2001, I got an introduction to somebody called Graham Ennis. I thought he was a UFO person, and he'd got what he called his Field Propulsion Conference at Sussex University. I was a bit apprehensive at the beginning. It turned out to be very good, and it turned out to have lots of what I call important people interested in field propulsion. People like Hal Puthoff were there. Alan Holt was there. And there were a lot of other people, if I could remember their names now, that you would recognize. But in 2004, that was the 3 years up, I thought we'd done a good program, but we hadn't made any breakthroughs. So it was very adventurous. It was a high payoff if we had made something, but it was very risky. Next slide, please. So in retirement, I thought we'd run a good program. So I sat down and I wrote a book. The first book I wrote was too long, but I trimmed it down, and then I tried to get an agent for it. Everybody, my children especially, tell me I can't sell books because I put equations in them. Okay, I went to 48 agents and publishers. They all said, no, thank you. One or two said, yeah, interesting, but no, thank you. So I persevered. Eventually, I thought, no, well, I'm going to self-publish. I want to leave a record of what we did, because I had the feeling that some thought that the people who had done it, and it had all been a part-time thing at Walton, none of us had been allowed to work on it full-time. We all had other jobs. And I thought, without the record, it's just going to be forgotten. So I wrote it. And before I knew what, I'd got an email from the publishers saying they'd been contacted by the BBC. They wanted to do an Horizon program. Horizon is a science program. It's very well known. It's got another name in North America. Actually, I'd been contacted twice before by previous editors. I didn't dare say yes because I knew the managers at Wharton. I don't know whether they're jealous or just they didn't like things like that being aired on the TV. Again, probably it was the link with Antigravity. So it was Steve Crabtree that contacted me. Was I interested? Well, I didn't work with BAE anymore and I had some other ideas. I said yes. He introduced me to his producer, a guy called Nick Young, and a lady called, I'll remember her name in a minute. Sorry if she ever looks at this. It's very rude of me. Anyway, the voiceover was done by a man called Peter Capaldi. Now, you might not know him in North America, but he's Doctor Who in the UK, very well known. He's the 12th Doctor Who. So Nick Young got his program together. I was interviewed in various places. So he talked about the UK Project Greenglow program. He then went to visit Mark Millis and learn about that. He wanted me to repeat the Lathwaite gyro thing that had got Lathwaite into so much trouble at the RI. I wasn't so keen, but he said, you know, this is not just a science program, it's also an entertainment program. So we did it. He went off to Moscow to see Podkletnov and learn about that. He talked about anti-gravity propulsion. Some people said it can't be right. In my view, some of the academics that he visited made statements that, to my mind, are wrong. I remember one said it's impossible because you can't have a warp drive because as a thing accelerates, it becomes, as the mass accelerates, it gets infinite in mass. But a propulsion system, a warp drive, has got a positive mass and a negative mass. And if you look at the mass equation, it's got a square root in it, Einstein's square root mass. Certainly the positive mass goes up till it approaches infinity when it's at the speed of light. But the negative mass is also negative infinity mass. And that approaches the speed of light and the two cancel out. On the way, of course, they've both been accelerating and radiating off energy. So he went to visit the people at CERN who had been looking at antimatter. And they were dropping anti-hydrogen. I'm not an antimatter person. It seems to me at the moment, the view is that antimatter has got positive mass, but the people at CERN will tell us whether it has or it hasn't. He then went to interview Scheuer, which is still in the news at the moment. Everybody said, no, that's not possible. So Mr. Dr. Scheuer ignored them like all good engineers and said, oh, well, I'll try it anyway. And he seemed to get a tiny effect. I should say that our photon drive also had a very small effect. Our photon drive was open. Roger Scheurer's is closed. Everything is inside. I've got some views about why it might work. Roger's got his own views. Other people have now tried it. I think Boeing have tried it, and I think other people have tried it too. There does seem to be something there. Nobody quite accepts the thing. In my view, engineers should try things like that, and then it's up to the mathematicians and other theorists to come up with the theory as to why it might work. Now, coming back to is it possible to use gravity to detect things? Well, the MOD have been working for a long time on a quantum accelerometer. At the moment, it can detect masses still in the meters, but you never know, in the future it might come up with something more. Now, the breakthrough propulsion physics, I forget when it was finished, 2002 or 2003, I think. Mark Millis has started his own thing now. And Greenglow one ended in 2004. So there was nothing in the UK, nothing in North America. And in Germany, for EU, Dresden University, they've started a program there. So that's still going. So Europe has now got a program. UK and North America hasn't, as far as I know. Right, now, what's the time? Am I all right just to continue on a bit longer, Tim?
Yeah, I would say keep going. It looks like you've only got a few slides left. So if you're able to just kind of push through them.
Next slide, please. Right, I put method of detection. So the first one, you'll know all about those. That's common ways of detecting magnetism. You might not recognize that long grey tube with a green laser beam through it. That's called Faraday rotation. I want to talk a bit more about that in a minute. Now, you can detect enforced rotation using a dry wheel. If you try to turn the flywheel round forcibly, you'll find it has its own deciding where it's going to go. And it's just vectors. So some vectors will tell you how it's going to move. There's something called a ring laser gyro, which was developed in the 60s and 70s. They're used in the aircraft industry for navigation, and telling you where you are and things like that. And that will also detect rotation. But you have to fix the device to the device you want to detect whether it's rotating or not, like an aeroplane. There's also a much cheaper device called a fiber optic gyro, which are now fitted in all sorts of systems. That can also detect rotation, but again, you have to fix it to the device you want to twist. Now we come on to gravitomagnetism, which we haven't really detected yet. If you use a sphere, it has its own gravitomagnetic dipole. It has its own angular velocity as well. But if you put angular velocity into a gravitomagnetic field, it won't interact. But the gravitomagnetic dipole of that spinning sphere will, if it's strong enough. It has a gravitomagnetic dipole moment, and this is what they did in the NASA Gravity Probe B. So they had to have a field that was strong enough that that could be detected by a spinning sphere. I'll talk about that in a moment. And then again, you could also use a ring laser gyro. I'll talk about that in a moment. Next slide, please. Right, so this is NASA Gravity Probe B, nothing to do with Greenglow, but it's interesting to me. If you look at the underneath that black rectangle, it says HE equals 1/4 pi, blah, 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 blah. That is the analog of a dipole from electricity or magnetism. So that's where it comes from. It's exactly the same, and you can get it. It's the moment of inertia of the Earth, the angular velocity of the Earth. The distance from the center of the Earth is r. So you can work that out, and it turns out to be very small. And what NASA was trying to do was detect the gravitomagnetic field of the Earth, and also that because the mass of the Earth's there, Einstein said it would warp Earth, and the NASA experiment wanted to detect the warp of Earth. And I forget when they sent the experiment up, but 2004, I think. It's not written on there, but it might be written here. Let me just check quickly. No, I can't see it. 2004, I think. So if you look carefully, you can see the Earth, gravitomagnetic field, that little tiny white circle with a red K underneath it is the spinning ball. It's got an axis, angular velocity axis, which is looking at a star. It goes round that dotted circle. As the Earth spins, that dotted circle does not move. In space, it's fixed. If it wasn't fixed, if that ball went round with the Earth, there'd be no magnetic field. That's relativity for you. So you need it to move. And you can see when we look in 2007, having done, it took 18 months to collect the data. So 2004, 18 months. It took another year and so to detect the space-time curvature, but they've detected it. The next thing they wanted to do was to detect the gravitomagnetic field. And you can see how small it is, 0.042 of a second of arc. And they managed to detect that in 2011. Now, as my technical director once said to me, what's the use of gravitomagnetism? It's too small, forget it. Well, looking at that, that seems to confirm it. We're not going to be able to create a gravity field from that. Anyway, we'll go on about in a minute. Look at the bottom right-hand corner. There's the Earth spinning, there's Australia, and at the very edge is New Zealand. And the people from University of Lancashire, Robin Tucker, and a few others at the University of Canterbury, they've got the world's largest ring laser gyro. It's fixed to the Earth, so it can pick up the Earth's angular velocity shown as omega E there. That's easy. They can do more than that. That omega E is like a spinning top. It precesses. I forget how big it is. It's about a meter or so. They can detect that oscillation of the Earth's like a spinning top, no problems. What Robin Tucker wanted to do is a spinning top, so it must have a gravitomagnetic field. Hang on a minute. It's not moving relative to the Earth. What the Earth is doing, it's spinning relative to space. So now we're looking at the other way around. As the Earth spins, it's spinning relative to the Earth, so it's spinning to space. So what they're trying to do is pick up the gravitomagnetic field of space. It will be the same as the gravitomagnetic field that the NASA experiment will try to detect. Next slide, please. Right. Now, this is a conundrum to me. When you drop a mass, we know it's weightless. If you're in a lift and it drops away from your feet, it accelerates downwards and you float. But if you look at that equation there, if you remember the GEM equation right at the beginning, it said if you could change the gravitomagnetic field, you create a gravity field. And it's that gravity field that we are interested in. But we had that permeability term, that what I call eta there. Now, I've also told you there's an equivalence between gravity and acceleration. But if you're going to cancel a gravity field, you can only cancel it with a gravity field, not an acceleration. You've got to have a gravity field cancelling a gravity field. So where's the gravity field? We look at that and we say, well, that eta there, sorry, that's my thing. I don't know whether you can see that. Has that appeared on your pictures? No. Right. Oh dear, what did you, right, it's gone. So I can write that out as the gravitomagnetic permeability in space outside the mass and the gravitomagnetic permeability inside the mass. Now, outside the mass is 10 to the minus 26. We can forget it. So that first term on the right-hand side is negligible. So although there might be a gravitomagnetic field outside, we can't detect it. For the whole mass of the Earth spinning, you know it was tiny. But what's going on inside the mass? It's got a gravitomagnetic field inside the mass too. Is the gravitomagnetic permeability bigger? How on earth do we measure it and decide? Because if we could make it big, we might be able to control gravitomagnetism, and if we can change it, we've got gravity. Next slide, please. Well, I don't know what the answer is. The thing about a falling mass is unstable. It's very difficult to model mathematically. The thing I know that I can do, because I can base it on an analog, I know about line charges, so I can do a mass charge. and I could drop it. And now it's steady because I've shown the big mass at the top there, but that's really that element in the middle of that line mass. And if it moves with a constant speed, I can work out all the values for the gravitomagnetic fields, both inside the mass and outside. And if you look about halfway down, I've written Hx equals 1 over 2 pi r, and it circles round. And I've written H int, which is internal, and that circles round. And if you go and look in your electromagnetism's book, you'll find what are called Biot-Savart laws, and they're exactly the same. Now, from our model of gravitomagnetism, we get eta, and that tells you that outside it's zero or virtually zero. Well, that's because the permeability, the density of free space acts almost like a solid. You might ask yourself, well, I can't see it. This is a question that people like Newton have asked, people like Maxwell have asked, and even people like Michelson. Why can't we see it? It's got infinite energy. We can't see it. Anyway, so if rho is infinite, that means the gravitomagnetic permeability is infinite. Sorry, is zero, because 1 over infinity is zero. And that is 10 to the minus 26 in real terms. And then if we look to see what the inside permeability is, we work it out, and we can work out what inside is going on. The induced permeability is V over R. Well, that's quite big. We should be able to measure that somehow. Even on a cylinder wall, it's the speed of it dropping over the radius of the mass. But how can we measure it? It's omega. Now, we know we can measure omega in terms of rotation. So we know when we are doing gravitomagnetic tests, we always know what happens because we can do the equivalent thing. A rotation tells you what's going to happen. So we know what's going to happen with gravitomagnetism, except it will be a heck of a lot smaller. Next slide, please. Right, I said I would mention Faraday rotation. So the picture on the left with that yellow solenoid, and I've got a glass tube, and I've got a green laser passing through a polarizer, making the laser vertically polarized, passes through a glass tube, and it comes out the other side through another polarizer. If I turn the solenoid on and create a magnetic field, it makes that linearly polarized light twist. So if you now look on the picture on the right, that is part of a conductor, a line. I'm going to pass a current I through it. And you know, as well as I do, create a magnetic field around it. This was first done back in 1820 by Mr. Ørsted. Right, so how can we detect that field? Well, you can use, now I've got to use something that's in line with that magnetic field, and I can use Faraday rotation. If I put, instead of having a line chart, that was a linear one on the left. Now I want to do it circular. And if I create a coil and wrap it round that thing and pass a polarized light in and then pass a current through it, it's in line with the magnetic field, so the line will rotate. Right, believe it or not, this is what was done at BAE. This was based on a Boeing, is Gary in the audience? This was based on a Boeing idea, and it works. So they used it in lightning trials. They would have a structure and they would pulse it with a very high electric charge, and they would use that fiber optic coil, work out what the magnetic field was, and from that, using those Biot-Savart equations, they could work out what the magnetic field was. Right, so now the question is, can we use the same idea to detect That was detecting rotation of a magnetic field. Can we detect rotation of a gravitomagnetic field in the same way? Well, magnetic fields and H fields are twinned anyway. We've already accepted that because charge E, when it moves along with mass E, so the two work together. Can we use mu metal to separate them? Don't know. Does Faraday rotation occur with gravitomagnetism? I think it must do, but is it big enough to detect? In fact, it makes me wonder whether the fact that whether Faraday rotation occurs at all might be because it's mixed up with Faraday rotation, with gravitomagnetism. And if you took the gravitomagnetism away, I wonder whether magnetic field would still cause rotation. I don't know. Next slide, please. I'm very keen, as you saw right with my early meeting with the universities back in 1990, Faraday's first gravity experiment. I was just looking in a book here, which is about Faraday, and at the end, it's about the Zeeman effect, which you may or may not know about. Zeeman was looking for the change in light when you put a magnetic field. So Faraday had a spectrometer, was shining light through it and getting all the various patterns, and then putting a magnetic field near it to see whether it changed. It didn't do anything. That was in about 1860 something. And Zeeman was looking through Faraday's diary and wondering, Faraday tried it. I wonder whether there's anything in it. He tried it, and guess what? With more sensitive equipment, he detected it. Well, there you are. So Faraday's mind was just amazing. He wasn't a mathematician, but he was brilliant at understanding what nature did. So this is Faraday's first gravity experiment. If you think of his induction experiment, it was very similar. What he did was put a coil round an object, a cylinder of something, iron, copper, or bismuth. He then attached a coil around it, and he dropped it because he thought, as that mass dropped, he thought that it's just possible it might create an electric current, and he would see that on the gyro. Just like his induction experiment, he thought it would only be temporary, so you have to be very careful to watch it. And his first experiment, it did do that. He thought he'd found something, but then he realized when he dropped a wire through a magnetic field, it created an effect, so he had to twist the wire. And when he did that, it didn't do anything. He spent some time doing other experiments. He never went back to this one. And I've looked at it and I've thought, I think he was probably right. That something does occur around it. Well, theoretically, it does seem to be the gravitomagnetic field. But how are we going to detect it? It's no good looking outside that mass. We've got to look inside. Now, inside, of course, is a bit difficult, but we can actually put the coil on the surface. The thing about gravity and gravitomagnetism, in the NASA Gravity Probe B experiment, they had to, that ball that was spinning, they had to enclose it in mu metal. They didn't want Earth's magnetic field interfering with gravitomagnetism. Gravitomagnetism is not shielded. Gravity is not shielded. We've only got one sort of mass, so you can't shield mass from outside effects, nor can you with gravitomagnetism. So if you put that fiber optic coil on the surface of the falling mass, what's going on inside the mass will create a gravitomagnetic field. You can't shield it, so it will get to the surface and it will be on the surface. It won't be outside the surface because that's where the permeability is so small, but it might still be there on the surface. So that's my idea for checking it. Of course, you don't really need the mass itself because the fiber optic itself has got mass. You could just drop a big coil and see whether there's any effect on polarization. So those are the two ideas. Is that the last slide? Oh no, next slide, please. So I think I'll read it very quickly. Have we got time? No, I won't read it. What I'm saying here is that Hans Ørsted discovered the magnetic field around a moving charge in 1820. We want to detect a gravitomagnetic field around a moving mass. If we can do that and start probing it in a laboratory, just like everybody else probed what Ørsted had discovered, we are going to be able to probe gravitomagnetism and work out how to change it. Once we can change it, we can change gravity and make gravity. That's the end. Thank you for listening.